Can you hear me? Can you hear me? Hello, Zoom people. Hello, hello, hello. Good. All right, Zoom people are happy. They make you happy. Good. All right, let's do it. Just a quick vote. So we have a tutorial next week, and we can either have the entire tutorial plus the quiz, or half tutorial and quiz. So it all depends on whether you're busy after your tutorial. If one person is busy, I cannot do it. So if somebody has, do you have classes after 8? Zoom people, do you have classes after Thursday? Would you like that? Is that a problem? Is it too late? Is it a bit too late? Yeah. All right. I mean, the first quiz is supposed to be easy, just so that you get the handle of it. But I know you need a full tutorial, so I'm like, okay, I will make a survey. Yes. Yeah, online. Yeah, yeah. It's good. All right. We'll see. I'll make a survey. I mean, you don't have to go to the entire tutorial because, like, the quiz is like 20 minutes or something. So don't tire yourself with the tutorial. All right. Anyhow, yes. Yeah, that's right. After 8. But I'll make a survey. We'll see what you think. All right. Today is the last day for review. I'm going to go over mean value theorem in Rn, vectors, Rn, and implicit function theorem. All right. So this is the, yeah. Yeah, so we saw this last time for R1. So instead of derivative, we have gradient. And just to remind you, gradient of f is equal to partial x1 f and partial f partial xn. Okay, and dot means dot product. So this notation means summation of partial fi dotted with vi. Okay, just a quick refresher. All right, so let's okay. All right, so let's apply it before we prove it. So here's a function. It's two-dimensional, and this is the Taylor formula. So the guy over here, well, I have it. I might as well show it. So the guy on the left, when v is v1, v2, is equal to this. The guy over here is 1. Is it clear why? Is it clear, right? Because it's E0 plus 2 times 0. Good. And we computed this last time. The gradient of f, we found it to be 1, 2. If you remember, we talked about this thing. So gradient of f at 0, 0 is 1, 2. Okay, so this is the Taylor expansion in multivariable. Okay, another way you might see it is with partials. So this is one partial of dfx1 dotted times v1 and dfx2 v2. Okay, either way is fine. But with gradient is more compact, right? Okay? Is that okay? All right. So the proof is identical. Oh yeah, a question, right. So what happens when V1 and V2 are small? What's the limit? What? Yeah, one. That's all right. It's just, I don't know, whatever. And it goes linearly fast, okay? Because this guy goes to one. So the speed is the speed is O V1, V2. Okay, put it in norm if you like. Is that okay? Because I will come back to this. I'll talk about Taylor expansion. All right, so it turns out that the Rn questions, how many questions in the quiz? I think you only get one with parts. But it will be one topic. There's 3 topics. We'll only pick one. I already picked the one, and you will know which one in the tutorial because I told him to do more questions. So, yeah. Right. Okay. Yeah, so the problem is 1D. So here's your function, GS, S is in R, and then you have X plus SV, and I'm going to apply mean value theorem to GS. So the mean value theorem in 1D, I'll write it again, says that you have X plus H is equal to G of X plus H G prime X plus theta H. Okay, let me write it underneath. Okay, so this is 1D mean value theorem. And so here we apply it for X0 and H1. You'll see why. This is like a small step. I know this might seem a little bit off, but we'll apply it right next to it. Okay, so when you apply derivative in S, so this is d ds, so this, so when you take derivative of f, f has vector input. Okay, so you apply derivative to each of the inputs. So that's why you have n derivatives. Okay, so let me remind you the formula for chain rule in Rn. So when you have f of g of, let me use a different notation. Let's say h of s, like this. Then this is the, I was going to say it. And whatever, I'll write the one I have here. So I1n partial f partial xi at h of s times the derivative of hi. Okay. Is there a better way to write this? I don't know. I mean, that's chain rule. Okay. Is that okay? So yeah. So F has inputs, right? So it has H1s, HNs, and here this is H. So HI is equal to XI plus SVI. So all we're saying here is take the ith derivative and then take the s derivative of HI. Okay? That's what I means. Take the ith component. Is that okay? It's just a review. There's nothing. So when you do that, let's forget this for a second. When you do that, you're just left with VI, right? Because X does not depend on S. So you have SVI over here. Is that okay? But then if you stare at this is a partial derivative times the ith coordinate. So you have dot product. Is that okay? Is there? Okay. So, okay, is there some confusion? Okay, okay. All right, so good. Now let's apply a mean value theorem in 1D. So f of x plus v minus f of x, by definition, is equal to g1 minus g0, right? Then from our mean value formula, it's equal to g prime theta, right? Right? No? So this is definition, and this here is the mean value theorem, right? Because what does it say? It says g1 minus g0 is equal to g prime theta, right? Okay. And we just proved that g prime of s, or if you like theta, is equal to this dot product. And that's mean value theorem. So we proved that f of x plus v minus f of x is equal to its linear approximation by the derivative. So when you move a little bit by v, you can linearly approximate by the gradient. So the picture you will always see is the following. This is f of x, this is f of x plus v, and this is the linear approximation. Let me write x plus v dot v. Okay, they're not identical. I mean, okay, let me just write f of x because they are identical. So when you take the derivative at x, you're almost close to f of x plus v. Okay? Is that okay? Yeah. Is x and v fixed for gs? Right. So another way to write this is g of x vs. Is that okay? Carl? Yeah, it's fixed. Okay, good. All right, that was it. So this is 1D mean value theorem. And we will apply it to get Taylor's theorem. Okay, so this is the picture I drew a minute ago, that you have f of x, and you have f of x plus v, and the gradient of f of x is O v close. Okay, so that's how good your Taylor approximation is. All right, good. So let's prove it. So this is the guy on the right hand side. Let me show you why. So you just move everything to the left from here, and you're left with this entire thing, right? Is that okay? You move everything to the left, and you want to show that this guy goes to 0 as OV. So I want to show this is 0. That's all. Okay, good. Yeah, I mean, we did this 2 days ago. So again, I apply mean value theorem. I have a common factor V, which I factor out. So I factor out my dot V divided by its norm. Okay. And then can someone tell me why is it 0 from here? What property are we using for F? Huh? Yeah, exactly. So we have that F is C1, which implies that all the partials are continuous. So it implies that gradient of F, x plus theta V, goes to the gradient of F of x as V goes to 0. Okay? That's the definition of continuity. Question? Okay. All right, good. All right, so now the main course of the dinner, Hessian. So this will be throughout the course. That's the main object. So I will go a bit slow here. I know you've seen it. I just want to make sure you remember. So the Hessian, denoted as this nabla squared, is the following matrix. Okay, so let me write a few terms here. So double square of x1, 1, double square of x1, x2, and so on, right? Okay, and then I can write one underneath. X2, x1. Okay, that's a n by n matrix because you have n derivatives. Is that okay? Yeah, this is not Jacobian. Jacobian is, yeah, exactly. Only, yeah. Yeah. And the Jacob, I mean, okay, let's, because people might be confused. Jacobian is, we really mean it for Jacobian when f goes from Rn to R, which is denoted like this. What is it in our case? It's just a gradient. Is that okay? Yeah, but the thing you saw there is when you go from Rn to Rk, then you have to take partial 1 of f1, partial 2 of f1, partial 1 of f2, right? And you go like, yeah, okay, good memories. So, all right, question, yes. Anyway, so that's the Hessian. And it's a symmetric matrix if you're C2. I will give you a counterexample, but you will never, in our case, it will always be symmetric because we look at C2 stuff. Okay, some cases you could have, I will show you later, that the derivatives do not commute. Yeah, anyway, so this is for C2. Let's do a computation. All right, and then because we will do tailored expansion, you will always see it in this form. So you will have V dot matrix V, with a vector V. Okay, so I will show you in the example if you don't remember. And this is called a quadratic form, and that's really our main interest. Trying to optimize this, and if you remember your linear algebra, you can minimize this by finding the eigenvalues. Okay, so should I do it? We'll come back to it. I don't know why I don't know. Maybe you remember that VAV, when it's an eigenvector, you get V lambda V, so you get lambda V squared. So when you want to minimize this quantity, you're looking for the minimal eigenvalue, like the smallest, like lambda 1. Okay, I'll come back to it. I mean, this is because we usually take V squared to have norm 1, Yeah, there's a lot of stuff here. So, okay, we'll come back to it. Anyways, just a reminder that we need linear algebra. Okay, let me compute this Hessian. Questions? All right. So this is your matrix, and hopefully it's empty, right? Okay, good. Can someone tell me what's the first entry? The 1, 1. Yeah. Yeah. Let me ask someone else. Yes. What about the? Let me get a tricky one. Yes, the fourth one, down bottom. Sorry, what? Yes, 4. Right. Yes, good. So this is 4. In other words, you can factor out your guy, and you have 1, 4, and what about here? Perfect. Is it invertible? Well, I mean, this is this is symmetric. So is it invertible? Oh yeah, it's not, because you have 1 times 4 minus 2 times 2, which is 0. Yes, good. Any questions? All right, so mean value theorem in Rn. You take C2, and then if you want to expand to second order, you end up with a Hessian. All right, so same proof. We can apply the R1 mean value theorem, okay, for second order, which we did on Tuesday. So that was the theorem that when you expand around 0 or x, you end up with the second order mean value here. Is that okay? Okay, good. Okay, now let's see where the cool stuff comes in. Now you have to do chain rule twice. Before we did it once, now we have to do it twice. So I'll do it step by step. This is what we got before, right? We had this from chain rule 1. And that's how it's simplified. So then, where am I? Yeah, here. So now I have to do it again. And I should explain how it happened. I don't know why I'm. Okay, so can someone tell me what happens when you take derivative in S inside? Why do I get a different sum J? I guess that's the question. Let me explain it, it's fine. So you have DDS of partial F partial XI, okay? Evaluated at X plus SV. But this guy is a function in itself that takes a vector to R. So you have to apply the total derivative to this. That's why the J comes in. So call this guy, I don't know, H, okay? So DDS of H plus X SV. And then I apply total derivative. So I get J1 to N partial Xj of X S V times Vj. Is that okay? Huh? Okay, good. Like that would be the hardest thing you will see in this course, just doing 2 chain rules. We're not very like, don't worry. So just keep track of the notations. That's all. Questions? All right. So yeah, but then you stare at this and you're like, oh, this is just the the quadratic form from before. Okay, because how shall I say it? And let me do it step by step. So if you just look at the ith sum, I don't know, it's not easy to see it. No, it's too complicated. But anyway, so this is V1 to Vn. This is the matrix with partials, F11, Fnn, and then this is V1, Vn. When you do the first, you get a vector, right? Can someone tell me what's the first entry of this vector? Just the first entry. When the Hessian acts on the vector. Can you just give me the first entry? Not all of them, just the first. How do you multiply matrix with vectors? Yes. Oh, huh? Yes, go ahead. Plus, right? Okay. Yeah, that's all I wanted to hear. Yeah. Okay, good. I wanted to make sure that people know how to do this. F1 V1 plus dot 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 F1N Vn, and then underneath is the second row, which is 2 1 V1 F2N Vn, and then F1 1 V1 Fn Vn. Is that okay? Okay, good. And then you just take dot product and you will get that thing. All right. Good. All right. Right. So then, yeah, how do we use this to get mean value theorem? So this is by definition. The next step is the mean value theorem, second order. So if you rewrite this, this should be a half here. I'm missing a lot of stuff. What happened? So this is a half squared, like this. Good. Oh, but I put h to be 1. All right, fine. So it's just 1/2. Let's put a half there. Okay, and then we just found, and this is g prime, my goodness. Oh. So g double prime theta is equal to this quadratic form. Okay, I'll fix this. So anyway, so we have f prime x plus a half v f of x plus theta v. Okay, is that good? I have it typed. I mean, I don't know why I'm. So that's the mean value theorem, that this increment can be linearly approximated, can be quadratically approximated. So again, the picture is you have f of x, you have f of x plus v, and now you can approximate with a quadratic, like this. And this is closer than the line. It touches it. Yeah. So, question? Okay. This is the f prime, if you like, gradient f and Hessian. Good. Can I go on? Yes. Yeah, this would be, I've made a lot of mistakes. I'll fix them. This is g double prime, a half. Yeah, I fixed it on the, I'll fix it out. Yeah. And there's a half over here as well. Yes, all over the place. Thank you. All right, so let's apply this result. First, I'll do our usual example. And from what you guys told me before, but let me do it again here. So we did this before. This was gradient of f dotted with xy. And we found this to be 1, 2 dotted with xy, right? Ex plus 2y. So that's how we get the second term. And this one, we computed it together, right? We had gradient Hessian of ex 2y was this matrix, right? Okay. So this is the quadratic approximation at 1 for ex 2y. Okay. All right. The proof goes as usual. We what do we do? Yeah, so we look at the guy on the, we move everything to the left, and we have to show that the guy on top decays as OV squared, so that this will be 0. So they cancel out. Okay, all right. So we apply a second order mean value theorem, and we get our half Hessian at theta, and we factor out the V's. So this is linear algebra stuff. We can go over it if you want later. Whenever you have a matrix, two matrices with a common things, you can write it as V A minus B V, and this is a difference of matrices. Okay, because matrices are linear. Yeah. Okay, good. All right, so we do this trick, and so we write this like this. So this is my A minus B. Okay. And yeah, how do I get 0? Yeah, C2. Good. Good. That's it. Questions? Right. So why do we need C2? Just an example to have it in your head, even though you might never see it in actual stuff. So you could have existence of derivatives, but it could be that they do not swap the derivatives. And that's the typical example you'll see. I'm not going to do it now, it's disgusting. But if you compute xy at 0 and yx at 0, you get -1 and 1. So the partials do not swap. Your Hessian is not symmetric. Optimization doesn't work with this stuff, okay? So that's why throughout the course, we will always assume C2. Okay. And we need symmetric, if you remember a bit of linear algebra, we need symmetric matrices because you have spectral theorem. Do you remember? Okay, good. Because we need our eigenvalues. We need to have eigenvectors, eigenvalues, so we can optimize. Yeah. And if your Hessian is not symmetric, you don't have spectral theorem. Yeah. You have Jordan blocks, if you remember that, but that's a difference. Yes, good. Good memories, eh? Nice. I love that course. All right, questions? Zoom people? All right. Now, another result we will use many, many times in Lagrange multipliers. is called the implicit function theorem. So, yeah, so let's go over this. The point is, this picture says that you give me some surface, f of x, y equaling 0, okay? Like, I don't know how to describe it, maybe like x and sine y, who knows? A bunch of stuff equaling 0, okay? So I don't know how to describe it, and plus it would be a branch function anyhow. But the point is, locally, I can describe it by a function. So this is FB, FA, and FC. Okay, so these are functions. Like this guy looks like log of x. This guy looks like, I don't know, maybe like sine going down. Anyways, you get the point, okay? So locally, we will go over the result that you can describe it by a graph of a function. Is that okay? Good. Okay, so why do we care about this? So in linear algebra, you solve this kind of systems. You had just linear coefficients and variables, and you wrote it as this matrix, right? And can someone tell me when do you have unique solution? What do you need from A? What? You said integer? What do you mean integer? Like 1, 2, 3 integer? Is that what? So when do we have unique solution to that system? Yeah, right? Yeah. You have to explain what you mean by integer. Yeah, so so if you have determinant to be not 0, A is invertible, so you can write x equal to A inverse B, and that will be the solution. Okay. All right, but we live in nonlinear stuff, and here's a system that you cannot even decide if it has a solution. Like, from computer science, there's like decidability, like NP, not NP. Yeah, I know it's disgusting, but the point is, this system, because you forced to have integer solutions, right? Sine is only 0 at, like, when is it 0, right? Pi x1 is 0. Whenever you have pi x1 is what? Do you remember? Huh? What is it? Pi what? Yeah, k pi, right? For k integer. So then you get that x1 has to be an integer. Anyway, so your x are forced to be integers, and it goes under the name of Hilbert's 10th problem. And they showed that you cannot even decide that it has a solution. You cannot even prove it. So this is all in numerical world. We cannot, mathematically is out of our hands. Yeah. Okay. It just shows you that when you come into nonlinear stuff, it's a wild world. Yeah, so we cannot decide. All right, but why do we care in optimization? So now let's come back to applications. So first, let me explain the system. Suppose you have a system of nonlinear constraints, like, I don't know, this could be like x1 square, y1 cube, same thing, xn square, y1 cube. All right, that's just an example. So why do we care about this system? So in optimization, you have the following situation. You have some variables y over which you optimize, such as market price. You don't want to sell bread too expensive, nobody will buy it. Too cheap, you won't make enough money. It's like a perfect middle ground. But you also have parameters like temperature, inflation rate, things that are changing, but you don't have control over. Okay, these are called like confounding variables. If you're taking statistics, like, right? Okay, anyhow. Anyway, so this is our optimization problem. You're gonna see this many times. We want to find the argument max, means the value at which f of x y star is bigger than all the f of x y for y in C, some set. Okay, Zoom people? All right. So it gives you back the extremum, where the extremum value happens. Okay, that's y star. Good. But now, what's the problem? The problem is y star is a function of x, right? X is fixed, right? So is that okay? So let me write it here. Y star depends on x. So as you vary x, you change the minimizer or the maximizer. Okay? So you want to know how this guy depends on x. So we will show by implicit function theorem that is a function of x, some g. Okay. But you can see why this is important, right? Like if the inflation rate changes tomorrow, I want to know how my y star changes. I don't want just a number, I want the dependence on x. We'll do examples next week, but yeah. Okay, so how do you get a system of equations? Take the y derivative. And what do you know? You know that at y star, you're maximum, so you're zero, right? So here's your system of equations. So this is the h1 equals 0, h and m equals 0. So that's what I mean. So you have a system of nonlinear equations. Okay? Is that okay? So to find y star, you have to solve this system of nonlinear equations. It's the same question. So we have, is that okay? Okay. So yeah, here we want to figure out y star given such a system. So you give me this system of nonlinear equations, give me some function that at least locally will satisfy this system. Okay, let's see what we mean by this. So you will always see this notation going back to second year. So this is a function from Rn plus k to Rm. So now you're going to get Jacobian matrix. And here's the implicit function theorem. So suppose this function is C1, and suppose that you at least found one solution. Okay, so the system I just wrote, suppose just by guessing or Newton's method, you found one solution. Now, you want to find an entire family, and you can do it if and only if you have the Jacobian matrix. This is Jacobian matrix. Is not zero. And why do you think that would be relevant? Because it tells you that the Jacobian is invertible. So hopefully if we have time, I will do the sketch. Okay, so that's why you will see, I will do a proof sketch to see why we need this. So that's all you need. And if you have this, it tells you that for each x close to your solution, you can find some f of x unique. So it is given by a graph that it satisfies the system. So this is really the core assumption. Okay. So let's see the picture. So suppose, let me do it again. So this is your f of x locally. Let me do it in different colors. Okay, and the rest is your so this guy is the surface, and it says that at least locally you can find an f of x, so that f of x is still 0 because it's inside the level set. Is that okay? So that's pretty cool because now you went from a 2D problem to a 1D problem. You had two variables, now you only have one, x and x. Okay. Shouldn't be that x that are not adjustable. Yeah, like, how do you say it? Yeah, like something, an x that you don't have control over. Okay, I will change the language, but the point is it varies, is a varying x. Okay, yes, thank you. All right, so let's do at least some examples. I will do 1D first. So take this equation, set it to 0, guess a solution using Newton's method. So at 1, 1, 1, we have that it's 0. Now, can you find a function f so that around 1, 1, 1, you can describe z in terms of x, y? So I can draw 2D. Just let me put 1, 1. And then I want to find so this is x, this is y, this is z, and I want to find f of x, y that is inside the surface. Too thick. Yeah, so it's inside the surface. It's just one of these lines. All right, so all you have to do is just take one derivative. Because, yeah, so here you don't have any vector value. You only have one equation. I will do one with two equations later. All right, so you take the partial derivative and the thing you want to remove. So you want to remove the z variable. So you take a derivative in it because we want to remove it. And then once you take derivative in z, what happens? This guy is 0. And then this guy, you do product rule. And this guy is 0. So you're left with this, right? And then you just plug in 1, 1, 1, which is not 0. So you have invertibility. So IFT applies. So yeah, so IFT applies because this is not 0. Okay? So it means that locally you can describe your function around 1, 1, 1. Okay, so I want to do the example actually. The proof, you're not going to be tested on it, so, but you will see the example. So let me just do the example. So now instead, suppose we have two equations. Okay? Is that okay? Now you want to you again by eye test or numerics, you find that the origin is a solution. And the question is, can you find some function f so that you can remove the UV variables? Okay, so again, let me repeat. If you can find this, you reduced your system down to 2 variables. Is that okay? Around 0, 0. Just to make sure we're on the same page. Good. So I have to compute the Jacobian. So I have to compute derivatives in u and v. Okay, this is called Jacobian. Is that okay? So I don't expect you to do it on your head now, but if you take the derivatives in u and v, you get this entries, and then you just plug in 0, 0, 0, 0, 0. And you get this matrix. So my question is, does IFT apply? Why? Huh? That what? Yeah. So we have -1 times 6, -1 times 8, and which is a number. Yeah, minus 14. So it's not 0. So yes. Good. All right. Thank you, everybody. Thank you.
How do we get from this one to this one?
Well, from here, the mean value theorem, G1, G0 is equal to G prime theta. Yeah, you wrote it here. Yeah, you wrote it over here. It's the same thing.
Like the G1 here is the. I understand we use this one, but
Wait, are you saying the first step?
Yeah.
Oh, the first step, yeah. The first step, you just plug in 1, and you get f of x plus v, and you plug in s0, and you get f of x.
Mhm.
Is that okay?
Mhm.
Oh, is that, you have a question?
No, I understand this part to get the G1 minus G.
Well, this is the definition of, like, if you plug in G1,
Right.
oh, sorry, okay.
Say the definition, but how do we get the G prime theta?
Yeah, this is the mean value theorem.
Mean value theorem?
Yeah, like a 1D mean value. Like, forget everything else, just from this.
Okay, so this is a.
We proved it on Tuesday.
Oh,
Oh, okay, I'm sorry, yeah. To in person, what? Yeah, we have to be online, yeah. Yes. Can you guys come closer? I can't hear you, sorry.
Sorry, no. Do we have tutorial this today?
No, it's, oh, yeah, right. Oh, it's gonna be today? Oh, no, but you're right, it's gonna be back to back to back.
Exactly.
That's insane.
Yeah.
Oh, my
After
God.
the in-person class, I might just have to sit here and just go online and do the tutorial.
That's funny.
Yeah, it's so weird.
Oh, you're right. Yeah, I mean, okay, I don't know what to say. Are you asking whether you can, what, sit here or something?
No,
or-
I'm just wondering if we have the tutorial.
No, not today, next week.
Not today.
Yeah.
Oh, also.
Yeah. I will ask him if I can book that. Thank you. Like we killed off uh, um, like remember our original problem is to optimize over x, y, but here you only have to optimize over f x y f of x y. So it became gxy, just two variables. Right, yeah. You can even find there's a, I mean, I didn't talk about it, but implicit function theorem gives you this little f as well. You can even solve for it by chain rule. No, this is the determinant. Yeah. No, it's like minus one times six. Yeah. Well, it just tells you that you can apply, sorry, it just tells you can apply, um, I mean, okay, I don't know how, like that was one of the assumptions. Like we needed the Jacobian to be, but it's so easy. Maybe I'll do it next time because like the proof is very beautiful. So you see next time? You have your x and your y, and then you want this guy to still be zero. So you set it to be zero, which gives you this system. And then by linear algebra, to solve it, you need this guy to go to the right. So you need this Jacobian to be invertible. It's like very stupid. It's nothing like, yeah. The determinant of this guy. Well, this one you don't even have to compute it. This guy doesn't have to be invertible. Yeah, but you never compute it. Like, I mean, you don't need to compute it. It will be like the zero matrix. You get a solution. The zero solution. It doesn't have to be invertible. Yes, so you can solve it like linear algebra. Ax is equal to p. Yeah. Yes. Focus on half is less than one. Half is shorter. Yeah, it's much shorter. Because half is less than one. Yeah. Yeah, but you're right. You're absolutely right. Right. No, no, so, no, like, okay, wait. We said the question was, when is this the biggest? And the big, because imagine you're on the unit sphere, and then the biggest is when the V is parallel to the gradient. Yeah. No, cosine theta will be 1. Theta will be 0. Yeah, yeah. Yeah. Questions? No, I will give you, I mean, if you want to prepare, this is the next problem, because it's going to take from here, listen on the syllabus. And then, yeah, and then, I don't know, like, I will change the page for the